Hello, my name is Sisingi and we are from IDP Group 3C. The project title is Production of Acetone by Dehydrogenation of Isopropyl alcohol. The project will be mainly divided into two parts, which are Principle of Chemical Engineering part and also Chemical Engineering Fluid Mechanics part. This is me and our team members. We'll start off with the Principle of Chemical Engineering part. First, we'll have a process flow diagram, which we produce from Microsoft Word. Now we'll start with the non-reactive unit operation. The unit we chose is a distillation column. First, we'll calculate the mass balance, and these are the assumptions we made for the calculation. Firstly, the total molar flow rate is set to be 1 mole per hour. Next, the isopropyl alcohol fat is 0.111 mole, the acetone fat is 0.44 mole, and the hydrogen fat is 0.444 mole. By performing the degree of freedom, we can obtain the value for the molar flow rate of the liquid stream and also the vapor stream. We can also obtain the value for the mole fraction of acetone and also isopropyl alcohol. This is the molar flow rate table where we will use the mole fraction of each component to multiply by the total molar flow rate to obtain their own molar flow rate for input and also output. By summing up the input and output, we can get that the total molar flow rate for input and the total molar flow rate for output is the same. Next is the mass flow rate table. Same as just now, but we'll take the molar flow rate of each component to multiply by their own molecular weight to obtain the mass flow rate. Lastly, we'll have our mole fraction and mass fraction table. For the mole fraction, we'll divide the molar flow rate by the total molar flow rate to obtain the mole fraction, and for the mass fraction, we'll divide the mass flow rate by total mass flow rate to obtain the mass fraction. Next is the energy balance. This is the assumption we made. For the reference point, we chose a same reference point for all the species, which is vapor state, 300 degrees Celsius, and also 20 atm. We created an inlet-outlet enthalpy table to help with the calculation of delta H. Since the value of enthalpy of isopropyl alcohol cannot be found in the table, based on the reference, we obtain that the enthalpy for the isopropyl alcohol is 30.2 kJ per mole. H1 and H3 equals to 0 because it's set as a reference point. Next, by using the formula, the values of the component can be obtained as below. Lastly, we'll calculate our delta H by using the sum of N out H out to minus the sum of N in H in, and at last we'll obtain that the value of delta H is negative 3.24 times 10 to the power of 6 kJ per mole. Next is our reactive unit operation. The reactive unit we chose is a reactor, and these are the assumptions we made for the calculation. First of all, there's 80% conversion of isopropyl alcohol into acetone. Next, isopropyl alcohol fat is assumed to be 88.66 kmol per hour. To calculate the mass balance, we first need to determine the amount of isopropyl alcohol consumed. We can do that by multiply the molar flow rate with the percentage of conversion. Then we can obtain the value is 70.928 kmol per hour. So we can know that the output of isopropyl alcohol is 17.732 kmol per hour. To calculate the acetone and hydrogen generated, we can use their stoichiometry relationship, and thus we obtain the value is the same as the isopropyl alcohol consumed. This is the molar flow rate table where the value is obtained by the previous slide. Next is the mass flow rate table. By multiplying the molar flow rate with their own respective molecular weight, we can obtain the mass flow rate for input and output. Then we have our mole fraction table, which the mole fraction is obtained using the assumption made by the non-reactive unit. Lastly, we have our mass fraction table. We can calculate the mass fraction of each component by divide the mass flow rate by the total mass flow rate. Now we are going to calculate the energy balance, and this is the assumption we made for the calculation. The reference point for all the species is set to be the same, which is vapor state, 100 degrees Celsius and 20 atm. As usual, we create an inlet-outlet enthalpy table, and as the value of isopropyl alcohol cannot be found in the table, based on the reference, the enthalpy of it is 6.338 kJ per mole. By using the formula, the values of the component can be obtained as below. At last, we can calculate the delta H by using the sum of N out H out minus the sum of N in H in, and we obtain the value is 1.85 times 10 to the power of 6 kJ per mole.
Now, I will be presenting our integrated design project, focusing on the pipeline system and storage tank design for the transportation and storage of acetone. our study includes calculation of flow properties, pressure drops, and strategy for safe product delivery. This slide illustrates the pipeline system used in our process. The pipeline plays a crucial role in transporting acetone efficiently from production to storage. We have carefully designed the system to ensure minimal pressure loss, optimal flow rates, and safety consideration. When designing our pipeline system, we considered various parameters such as pipe dimensions, pressure drops, flow rate calculations, and material selection. The goal is to maintain efficient fluid flow while minimizing energy losses. Next, we will look into the specific dimensions and flow calculation of one of the pipelines in our system. These slides provide an overview of pipe dimensions and pressure drops across the system. Understanding pressure drop is important as it affects pump selection and energy consumption to ensure accurate prediction. We have made a few assumptions for our calculation, which are outlined in the next slide. For our pipeline calculation, we made the following key assumptions. The first one is steady flow rate throughout the system. And the second one is incompressible fluid flow, assuming no significant density changes. And the third one is the fluid has one-dimensional fluid flow, meaning velocity varies only along the length of the pipe, and the pump efficiency is set at 85% to account the real-world energy losses. This assumption helps simplify our calculation while maintaining realistic estimation. Here, we present an example calculation for pipe 9, which demonstrates key flow properties. The first one is mass flow rate. Using the molecular weight of acetone and the given molar flow rate, we calculated the mass flow rate as 0.8583 kg per second. And for the volumetric flow rate, by dividing the mass flow rate by the fluid density, we obtain 0.001095 meter cube per second. And for the mean velocity, using the cross-sectional area of the pipe, we found the velocity to be 0.2297 meter per second. And for the Reynolds number calculation, we used the formula, and this resulted in Reynolds number equals to 45,845, which indicates turbulent flow since it exceeds 4,000. Since the flow is turbulent, we need to determine the friction factor, fitting loss, and total friction loss to estimate the pressure drops. To quantify pressure losses, we use the Colebrook-White equation to calculate the friction factor, which is 0.005802. Additionally, we accounted for fittings and entrance or exit losses, summing up to total friction loss of 0.2451 joule per kilogram. By applying Bernoulli equation, the final pressure drop across pipe 9 is negative 0.1922 kilopascal. This result helps determine the required pump power and pipeline efficiency. In addition to pipeline design, proper storage and handling of isopropyl alcohol is crucial. We have selected polyethylene as the storage tank material due to its corrosion resistance, structural durability, and ability to prevent contamination. Maintaining optimal pressure and temperature in the storage system is essential to prevent undesirable chemical reaction or safety risks. The storage tank was designed to accommodate the daily production of 83.409 meter cube per day. To ensure safety and handle fluctuation in production, the maximum capacity of the tank is 101.79 meter cube. This design minimizes the risk of overflow while ensuring an efficient storage process. In conclusion, our project successfully demonstrates the efficient design of a pipeline system with controlled pressure drops and optimized flow rate, and the importance of material selection in preventing contamination and structural failure. I think that's all from our crew, and thanks.